Hi, good evening, everyone. Um, Very warm welcome to yet another part two of light and electron microscopy, yet another session. I was actually on my cycle, I'm going for cycling in the evening, and there was a lot of traffic plus in the street. There was traffic and cycle, and I usually come by 8, 7:45 at my house, but due to just traffic, I just wrote 10 minutes before the message that I might be late. But no worries, we continue further then. Slowly students are getting joined in, but not so much like it used to be earlier days. So at least we should have 30 students of 35. Okay, let's start then. So yesterday we discussed about various types of light microscopy, under which we also discuss its various figures, how the pictures looks like under them. For example, polarization microscope with the minerals, crystallines from meteoroids. Then we discuss from phase contrast microscopy, how the different cells of squamous epithelium cells looks like. Then dark field microscopy, under which we have discussed about spirochete and hydrodacaton reticulatum, in which the background is dark. Yeah. Then we discuss about inverted light microscope, bright field microscope, where your light is coming from top and your objective at the bottom. Then we discuss how the images looks like in the light bright field, that there's a bright light in the background will be coming up. And then, yeah, this is, we just started the basics and we discussed the more about basic concept of uh, how ethical science should work, how an ethical researcher should work, how we should work as a researcher. So that was the recap. Now let's start with epifluorescence microscope. Yeah. So epifluorescence microscope, this allows actually detection of molecules and ions within the cell. So earlier it was everything is possible from outside the cell, but now it's possible within the cell. So if fluorescent dyes absorb short wavelength of light and emit longer wavelength, and barrier filters and diachroic prism elect the excitation wavelength that strikes the specimen, exclude the excitation wavelength from the detector. So we use as a light source mercury xenon arc lamp as a UV light source. Yeah. So we have a not the like white source in this, but a UV light source, and it's also give very high contrast, high resolution images. Background remains black in them, and no condenser is required. Lights come from above the specimen, and multiple fluorescent probes are available and detect small quantities molecules. Can use antibody staining technique. So this is the image of tetrahymena, the apple fluorescent images. We can see in this technique, and the specimen is probed with the antibodies that binds to the molecule, and the secondary antibody is labeled with the fluorescent dye that are used. So first we add a primary antibody which attaches to the various molecular cells part. Then on the top a secondary antibody is added which is in fluorescent nature, which emits light in the dark. So that's why we see a in the dark background a brightened field image. So for example, in this tetrahymena, this is a ciliated protozoan. So with the help of fluorescent dye, that is uh, fluorescein isothiocyanate. Just a second, someone is there on my door. Hey, coming back, students. Okay, sorry. So in this image here we were the tetrahymena, the immunofluorescence of tetrahymena, which is a ciliated protozoan. So we used this fluorescent isothiocyanate, yeah, which emits green light in the dark. So above left is the stains, and we can see here is stained with the anti-basal antibody, and the right one is stained against the cell membrane surface antigen. This is for the whole basal body. This is for the only cell surface antigen. So compare the information obtained above using the fluorescent technique with bright field view of tetrahymena. So and the right hand side is a bright field, the light microscope, yeah, with simple hematoxylin that is we use in the hematology lab. So the simple staining in this case, but this is the one with the cell membranes are stained here in the basal body. So what differences in these three images we can see is that there is a very nice parallel formation is happening, and then there is a curve we can see. Where on the cell membrane we can see this microtubules like structures, spider web like structures coming outside, which is not similar to that. So of course the cell membrane is different from the basal body, and whereas the fluorescent, this light microscope bright field view of the tetrahymenas is of no use actually. We can mainly see just a nucleus in the center and a shape morphology, but we cannot say anything about cell membrane or basal body, how the Golgi bodies are, how the mitochondria, we cannot predict anything. So that's the thing. The more your the more advanced your microscopes are, the more advanced your techniques used, the more cleverly used your experiments, yeah, in order to identify your results, the more far would be you are near to your question that you're looking for. So for every question, there is one technique to answer that scientists have discovered so far. Is just you have to find out for which question which technique will be the best. Now this is also another image, the epifluorescent image. So this is one of the this is one of my I like the this image is one of my favorite one. This is showing the metaphase in the lung cells. Yeah? This is showing the metaphase. So here we can see three fluorescent dyes are probed. Yeah. So first is specific DNA, that is keratin, yeah, and tubulin. So DNA is there, keratin is there, and tubulin is there. So blue one, we can see these chromosomes are metaphase chromosomes, the blue one. and the red one are the keratin filaments outside these microtubules, and the yellow one is the spindle apparatus of the microtubules. Yeah, so this is from the spindle fibers. Outsides are the keratin filaments, and this one is your chromosomes and the metaphase stage in the central plate of your cell, and both are being separated. We can see this, and the best part is when you do the live cell imaging, you can see this happening in front of your eyes. These one cell will be dividing into two parts, spindle apparatus getting separated and making a new cell membrane, and yeah, making something two lives from one. And this is only possible because of using this advanced technology and the epifluorescent microscope with the blue dye, with the yellow dye, and the red dye. So that was about epifluorescent microscope. Yeah. Now, as you know, scientists find one thing, and they tend to go what it's like. Okay, we have discovered one thing. Now let's go more advanced. So whatever the other techniques we have discovered, let's join them together. Yeah, so what they do is, okay, someone has polarizing, someone has dark fluorescent microscope, someone has epifluorescent microscope, someone is doing, yeah, something new technology is bringing. So why not we join them together? So that's the example of your differential interference contrast, DIC microscopy, also called as Normarsky optics. So in this, we have a mercury lamp, yeah, a polarizing filter, recombining prisms, and beam splitter. Also another Wallstone prism is there. So it's a very, by the picture it's looks very complicated, very thick body tube, very thick base. Many new things we can see are added into this microscope, and so this microscopes actually have capability of both epifluorescence and DIC capabilities. So both are possible within this microscope. So as I said, so as the technology develops, as the things are developing, so people tend to bring all the latest technology and add into the one thing only. So it's like in the televisions, we used to have only Doordarshan before. Then cable came, yeah. So when we have these dishes, big dishes, in earlier, like in 90s, so there used to be dishes of the size of whole, like your whole half of your terrace will be covered with that dish, and only then you get 4 or 5 channels out of it. But now those dishes become very small, this Tata Sky and all, so it's very easy to see many channels within that. So within that, then this dish TV came, then started to come about cloud TV like Airtel and Netflix and all this. So everyone is dependent on them. So there was different things were there. So what came out at the end? Then came out your smart TV. Yeah, then came out your smart TV, which has everything. You can use your mobile out of it. You can play YouTube on your smart TV. You can watch your all sports channel in HD via dish channel. You can watch Netflix. You can watch YouTube. You can even connect your PlayStation to watch that TV. Yeah, so or Nintendo is also hit nowadays. So you can do whatever you want to do with the television. But my recommendation, in your room these things should not be there. Of course we need some enjoyment in life. Of course we want something to relax our body, but these are actually, even myself, I'm using lots of Facebook and Instagram, YouTube, most of my time. So I have tens of books to read on, but I'm so, like, what shall I say, addicted to these, that I cannot stop that. So all these things, these media, social media, and things that we are having, they are meant to be addictive. They are meant to be addictive with the help of your artificial intelligence and all these. So once you started to like something, the next picture will be, the next link would be something that you like. Nowadays the reels are coming up. So once you finish one reel, next reel is coming. So this was started by TikTok, and then it went to the Instagram, then it went to the Facebook, and it went to the YouTube. if you see these reels, they are everywhere. Why? Because people get addicted towards them. They can spend lots of time on them, and you get nothing out of it. You get nothing, zero. Just think about it today. So what I just said, in order for productiveness, if someone is preparing for some entrance exam, or looking for a career in research, or in the final year of PhD, or in second year of MBBS, or something, anything. So I'm just sharing my own experience. Yeah, I get nothing out of all of this. I mean, there's no profit. I'm not gaining. Yeah. If you're watching a Netflix, if you're watching some motivational movie, like I watched this movie called Founder, that how McDonald's was discovered. So how the person was so hungry to become big, he took the idea of two brothers, and then started to go another way. It was wrong, but this is how it is in the world. So now let's come to the science. So the main reason here to talk about all these topic was actually to discuss that in the scientific world, people see that what is in at the moment, and they bring all those ideas and they made into one, so that people could don't have to buy separate 3 or 4 products differently. They can have the one product itself. So they resemble phase contrast but more sensitive and give very high resolution. So as we are going up to these microscopies, so things are getting better and better. So they are also using polarizing lenses, like in the polarizing microscope, and therefore we can quantitate our data. And halogen light beam is also polarized and split by the beam splitter and passed to the specimen. Then the second prism is also there to split these beams. So any change in light wave due to passage of specimen cause interference, and this could be read by the refractive index. So they provide actually 3D images. They are the first one who provide 3D images. Very high numerical aperture, high contrast, excellent resolution, good for unstained specimens, live mounts, and can see membranes within the cells. And they detect changes in the refractive index of specimen. So this is one example of DIC fluorescent images. So um, so in the top one here, what we're seeing is the ovariole, the oocytes of cricket, the insect. So here, the O, big O is your showing the oocytes, and N is your oocyte nuclei, and B is your Balbiani bodies, also called as mitochondrial clouds. And this is in the B part. In this figure, what we're seeing is also the same figure, but the Balbiani bodies are more prominent here. Yeah, they are more coming good. So epifluorescent images of Balbiani bodies stained with the rhodomine 1, 2, 3, and fluorescent stain specific for the mitochondria. So this is the epifluorescent image, and this is the DIC image. Yeah. So DIC image we can see straightforwardly from the epifluorescent image. It's more things we can see bulging out. The cells that we are seeing here, we can see the proper structure, proper curves are coming up. We can see these bulges upon top. We can see these Balgiani bodies on top also. It's like a moon, moon in 3D. But here it's like you're taking a 2D photograph with very old camera. So that's the difference of DIC images. Now comes the most prominent and most happening and most usable. Uh, it's like I could say Amir Khan or Shah Rukh Khan in microscopy, the top-notch microscope that we go for. Once you do your experiments under light microscope or epifluorescent microscope, polarization microscope, once you get your details on that, so in order to get published high impact fact paper, in order to get better results for the scientific world, for the academia, people tend to go for laser microscopy, confocal laser microscopy, which is principle is based on the electrons. Yeah, so we put this laser made up of krypton and argon, which has a very high resolution, sharp images are provided, very sensitive. and it eliminates all the background interference that are present, and they are connected towards your computer, and you can yeah, play around a lot with it. There's a lot of options you can do which might be not possible in previous microscopy. So so confocal laser scanning microscopy is mainly based on the specimens, which check that there are specimens in the horizontal plane, that is XY plane. So only light from the plane of focus reaches a detector, and the scanned image is digitally recorded. So images from consecutive focal planes can be recorded, and composite or 3D images can be digitally created afterwards. So this is the confocal image um, of trichomonas. Yeah, and this one is the bright field trichomonas, we can see with the posterior flagellum. In the green is showing the exostyle, and the red are the unstained one. So here we can the stained one, this one, very nice figures here, and this is in the bright field microscopy. And the same thing when we did in the so someone who is expert in the microbiology with these microbes, for them it will be very interested. So here we can see this is the optical sections of 13 trichomonas immunostained with antitubulin and FITs. We say this fluorescein isothiocyanate, a short form of FITs. So somebody asks, if you ask in the lab, I want to stain my samples with a fluorescent dye. So we don't say fluorescent dye, we just say FITs, FITCE. So these green structures, they are consisting of microtubules, and the PF that we are seeing here is your posterior flagellum, and the AF is your anterior flagella. C is your costa and exostyle, the red arrow. So they are compared with the bright field image to the right. So these are the photo given by the B. Estridge. And yeah, remember, whenever we are taking any, yeah, I didn't give the references here. So like here, this was image was taken by Bethesda MD, image by Ryder and Hugs, New York State Department Health, Albany, New York. So always try to give a reference. Yeah. So from wherever you have taken the image or any figure that you are putting up, even in your references you are taking from Google or anything, try to give every time the reference. So it's like this image, let's say Akarti and Sukarti, they are two students, very close friends in the Department of Biotechnology, and they are in the final year of PhD students. Yeah, and they did their whole PhD to find this structure, and it was very hard. There was no microscope, there was no dye till that time. Nobody knows about that we can see this these things with our naked eye. But Akirti and Sukarti, they discovered microscope, they discovered these dyes, they discovered mitochondria, they discovered everything, yeah, from zero. Nobody knows about that, and they define these terms, they give these names by their own, right? And uh, and they got Nobel Prize winner also for that, Akarti and Sukarti. Yeah, so in 2000, let's say in future in 30, right? So they got Nobel Prize winner for the same. And what happened is that in 2040 somebody took these images and they didn't recognize those people who have find it out. So it will be very, blunt and very embarrassing situation. It feels bad that if you do not give a reference to someone who have discovered with very lot of hard work in that, and we just use them for our own use. Yeah, so this is one of the other ethical part in the science to be a good researcher. Always give reference from whom you are taking any data or any line or any quotes, yeah, any figure. Always in your presentations everywhere try to give their reference towards them. It's always good, always good. So this was all about so far. confocal microscope. Yeah, so this was all about confocal microscope. So we have discussed so far. Now the light microscopy is done. Now it's time to go for electron microscopy from here onwards. Yeah. So as we have discussed in the yesterday lecture, that electron microscopy, it's of two type, that is scanning electron microscopy and transmission electron microscopy. Yeah, scanning electron microscopy and transmission electron microscopy. Let's take one by one. In the scanning electron microscopy, we have a fixed dehydrated specimens that are mounted on the stubs. So we use stubs here on which our specimens are mounted, and we coat them with the gold or palladium or rhodium. Any of the three things we can use: gold, palladium or rhodium. So it's a bit expensive, these kind of microscopy. And the specimen is placed in a vacuum, an electron beam then scans back and forth over it. Yeah. So first we dehydrate it, we remove all the water from it, and then they are mounted on the stubs and surface coated with the gold, palladium or rhodium. The specimen is placed in a vacuum, so an electron beam scans back and forth over it. Then electrons that bounce off the metal coated specimen surface are collected, converted to a digital image and displayed on a TV like monitor. Right. So electron beam is focused using a magnetic field, and scanning electron microscope provides a 3D image which gives information about external topography of specimen and much higher resolution and magnifications than possible in the light microscopy. So here you can see the magnificent images of your scanning electron microscope on the top, and the bottoms are the DIC image. So we are just checking the comparisons between two microscopy. So this is DIC microscopy, this is SEM, which reveals the surface topography. So much greater detail is obtained using SEM because of greater resolution and magnification capability. So this is scanning electron microscope. On the top left is the trichomonas, and in the right is the tetrahymena. This is tetrahymena and this is trichomonas. The same, this is for the DIC image from the trichomonas and the tetrahymena. So just look at these images. So this is very nicely, these 3D images are there. So this flagella being there in this flip-flop fashion, and on the other side your tetrahymena showing these very nice 3D structures outside. So which was in the normal microscopy, we can just see the morphology of them. Yeah. So this is the highly advanced technique, and whatever you are looking for, you can get the answers out of it. Then transmission electron microscope, this is also in this, we fix, dehydrate our specimens, we harden in sections stained with the heavy metals in them also, like uranium or lead, and then insert it in the electron column. Then electron beam is absorbed and deflected by these heavy metal stains, and shadows are cast onto the film or fluorescent plate. So in this we get 2D images, and so earlier in this case in the scanning electron microscope, as you can see, we can see very nice 3D images basically. So this was providing a 3D image from all the angles. But in this case, but it was not able to reveal the internal structures, internal organelle. But in this part, it could reveal, though it's give it 2D images, but it will reveal the internal structures. Also give high resolution, high magnification, and electron beam is focused by the magnetic field. So here we can see the trichomonas, this is SEM left and this is TEM of the same. So SEM could show the external structure visible, whereas the TM we could see all the internal structures. So N for the nucleus, yeah, G for the Golgi, this is the Golgi, and then hydrogenosomas, this one, then F for flagellum here, this one, yeah, and so on. So that's the beauty of your difference between your TEM and SEM. So as TEM gives a internal structure, internal structures information, whereas SEM gives the outside structure, but it's give a what you say 3D image of it. So that's the major difference between your SEM and TEM. Yeah. So we are done with the basics of your light and electron microscopy, how the images looks like, what is the major differences between them. Now we will take this session further in order to understand how we fix these samples, how we to use these for these microscopy. If we have we cannot just straightforwardly we have the tissue, you know, from the heart cell or liver cell, and we straightforwardly go to the microscopy and start analyzing it. So it needs proper 1 or 2 day of protocol in order to fix them with the dye and able to see them each thing yeah, for the visible fashion for the scientific world, right? So some more TM images, 3D images we can see from the pancreatic acriginal cells in the right and the rat liver cells in the left. So they reveal the internal cell structures. N is for nucleus, and U for nucleolus, and ARIA for rough endoplasmic reticulum, and CB is your cell boundary, right? And zymogen granules and mitochondria. Mitochondria, nucellus, nucleus, rough endoplasmic reticulum, zymogen granules, the cell boundary is there. So yeah. Now let's go for specimen preparation for light microscopy, scanning electron microscopy, and transmission electron microscopy. So general characteristics for preparing specimens for light microscopy. For light microscopy, if you have live cells which are alive, so you can just watch them, just view them, or you put some vital stain to them and then view them. Otherwise, if you want to preserve your samples for the long term, you go for histology section. Then in that there are 7 steps. That is, you fix your samples on the slide, you remove the water, dehydrate it with the chemicals, then infiltrate and embed them, and then you section them, and then you mount and stain, and then you view them. So in these 7 ways you can see the things in the light microscopy. So live mounts to view organisms, tissue or cells as close to the natural state as possible. So unstained live mounts are used. So viewing time of the live mount is limited, and unstained specimens have low contrast. So supravital stains may be applied to provide more contrast or identify certain components, and these are stains that are not harmful to the living cells. So they are fixed or preserved specimens for histology, the study of tissue. So specimens may be preserved using chemical such as formalin, acetic acid, ethylene or methylene, and fixation immobilize the cells such as your proteins and lipids. And fixed specimens are dehydrated then by serial transfer of ascending alcohol series to 100% alcohol. So you do like 70%, 80%, 90%, then 100%. Then you infiltrate the sample with the melted paraffin or substitute of that, and then you mold to the hardened substance. Then specimens are cut into the 5 into 10 micromolar thick sections using steel knife or razor instrument called microtome. So this is a vibrotome. So you put your sample here and it will cut for you with the knife holder. Then sections are mounted on slides and stained to achieve contrast or identify cell structures or components and viewed microscopically. So let's watch one microtome technique. So you embedded tissue samples with paraffin wax.
Assuming you've already harvested and embedded your tissue samples in paraffin wax, obtain your paraffin cartridge from the refrigerator. Next, uncover the microtome. Next to this machine, you should find the slide former. Plug this in and adjust the dial to the middle position. Place a beaker of warm water on the slide warmer and keep a transfer pipette within reach. Next, remove a blank slide from the box and label it with your initials, organ type, and date. Place the slide down on the warmer and using a transfer pipette, put a few drops of water onto the slide. This series of steps involves paraffin cartridge preparation. Remove excess wax from the cartridge using a razor blade. Make sure to cut it in a trapezoid shape with the longest edge at the bottom of the cartridge. Be careful not to crack the paraffin. When you are ready to section the paraffin embedded organ, place the paraffin cartridge in the microtome while pulling the main handle towards you. Use the knob on the right to adjust the section thickness required for your sectioning, approximately 10 microns. Next, adjust the stage with the wheel on the left as to move the paraffin cartridge close to the microtome blade. Unlock the wheel on the right by pushing the pin button down. Next, place both hands on either side of the finger guard and pull it down as to reveal the microtome's blade. Remember to always lock the wheel into place when you are not sectioning. As you begin to cut into the paraffin specimen, discard all unwanted sections using a paintbrush. Be careful not to drag the brush across the blade. Continue turning the wheel until you obtain a desired section. Once you have done so, make a ribbon that contains multiple.
So here you can see this is our sample. This small dot you are seeing is from the mouse, one kidney or any tissue that you want to see under the microscope, and this has been embedded into the paraffin wax onto this plastic box. And then there is a blade here, and this is a machine which moves up and down, and this blade is making these thin sections of 10 micron, and these sections will be put over the slide and we will fix them with the help of histology experiments.
Multiple sections of your tissue. Use tweezers to lift the ribbon from the microtome. Place it on the bubble of water on your labeled slide. Repeat making ribbons and making slides until a desired amount is reached. When you are finished using the microtome, place the finger guard back into position and remove the paraffin cartridge. Use a paintbrush to thoroughly brush away excess material. Clean area and cover the microtome. As for your slide sections, allow water to evaporate, but do not keep slides on the warmer for extensive time periods. This will ruin your specimens. Lastly, unplug the slide warmer, Put slides away for safekeeping and finish cleaning the area.
So that's very specific, very simple, and this is, but they are showing very old style of microtome actually. Yeah, in 2012 I used them. Actually I used them in 2012 also, but in my case it was more advanced. It was water was going through automatically. I do not have to put water on slide. Yeah, I was in Max Planck also at that time. That's how you uh, make your. Okay. Now what's next? So now we will discuss about histology, or is it there? No, no. So mainly we are discussing about the sectioning, how we do the sectioning. Then systematic for preparation of your scanning electron microscope, how you prepare sample for that. So for that you need to fix them, dehydrate, then we mount on the stubs. Yeah, so as we discussed, we have the stubs, then spotter cord, and then we observe them. So you fix your cells with the glutaraldehyde, paraformaldehyde, osmium tetroxide, then dehydrate them with the alcohol series from 100% alcohol to non-water. Then you put organic solvents such as acetone or propylene oxide. Then specimens could be critical point drying apparatus, yeah, in that. So these are the stubs, looks like a pen nail, and they are mounted on the aluminum stubs using sticky tapes. So applying specimens to stubs arranged in the holders here. So coater coats the specimens with gold, palladium or rhodium, and a special chamber to cover the specimens with 10 to 20 thick metal layer. So after the sputter coater is done, you put your sample into the machine, the specimen insertion. Then electron column is there. Then electrons will be strike over your sample. Then you can see your image um, in this computer. And for the transmission, it's also the same. You dehydrate, infiltrate, section, apply section to grids, then you stain, and then you observe them. So in this fixation, we do the same: paraformaldehyde, glutaraldehyde. For dehydration, same method: alcohol series, then organic solvent. Then for infiltration, we use epoxy or plastic resins that are placed in the plastic molds to harden. So in these molds, we put our samples, specimens, and blocks are removed from the molds later on. And then also afterwards, we use ultra microtome here. Is even far better than the microtome that we used earlier. So here the glass slides, here we can see there's a water already in the slide here, and this ultra thin section 1 millimeter wide. Earlier we had 10 micrometer wide, but this is even less. This is the knife is there, and then you can see your specimens in very nice way here. And then you put your sample onto this tiny metal grid for the sport, and then you can this one type grid, and you put your sample into these crossings with the help of your forceps. So heavy metal stains such as uranyl acetate and lead citrate are applied to make certain structures electron dense. So this is how TM looks like. This electron column from the top, specimen insertion, additional image display could be seen there, and then phosphorant plate for viewing the image. So that's it. We'll enable to see your samples, how to fix them, how to see them. So how to use microtome. So I will share these slides with you now. Yeah, it will be sent to you. It's a big file. So okay, thank you very much. We are done for today, and then tomorrow we will start with the animal cell culture. Yeah, more about animal cell culture, and we go deeper about it. So until then, thank you everyone for being there. Hit subscribe button, hit like button, share these things within your friends. So if somebody could also be benefit out of it, why not? Yeah. So thank you very much. Take care. Wish you all nice evening. Yeah. Have a happy Wednesday then. See you. Blessings. Bye bye.